Hi guys, so in this video, we will be covering truss analysis, specifically analysis of your plane trusses. Now what is a truss? A truss is a structure composed of slender members joined together at their endpoints to form a rigid structure. When members of a truss lie in a single plane, it is called a plane truss. Now typically, your plane trusses are used to support your roofs and your bridges. Now, as stated in our definition, your trusses must be rigid to prevent the collapse. We have an example of a frame here, frame A, B, C, D. And if we applied a load on joint B, our framework has a tendency to collapse. Therefore, it is not rigid. The way we could make this framework rigid is by adding a diagonal support right here. Now, please note that the simplest framework that is rigid or stable is actually a triangle. Consequently, your simple trusses is constructed by adding or by starting with your basic triangular truss and adding members to it. Alright, so let's proceed to the assumptions that we need to make in order for us to determine the forces developed in each member when the truss is subjected to a given loading. So the first assumption is that the members are joined together by smooth pins. And the second assumption is that all the loadings are applied at the joints. Now because of these two assumptions, each truss member acts as an axial force member, and therefore the forces acting at the ends of the member must be directed along the axis of the member. If the force tends to elongate the member, it is a tensile force, whereas if the force tends to shorten the member, it is a compressive force. Now, if we look back in our previous lectures, we'd know that in order for us to classify a member to be a two-force member, there must only be two forces acting at two different locations on our member, and these two forces must be equal to each other, and they must be acting opposite each other, and they must be collinear. Therefore, all the members of our trusses are actually two force member that are actually loaded, or there are axial two force members. That means the forces acting on the ends of our members can only be either tensile force or compression forces. Typically, in our truss analysis, we would assume that all the members are going to be under tension. Therefore, if when we solve the forces in our member, if the result is positive, it is under tension, and if it is negative, it is under compression. We'll talk more about this when we discuss the different methods on how we analyze stresses. Okay, so let's get a quick run through of the different components or the different terminologies that you might encounter in the problems for the board exam. So, the members on the top of our truss is what we call a top chord, and the members on the bottom of our truss is what we call the bottom chords. And then the members in between your top chord and your bottom chord is what we call the web members, or simply the web. Alternative names for webs: if you have a vertical member in the middle of your truss, it is sometimes referred to as your king post. And all the diagonal members between your top chords and your bottom chords are sometimes referred to as a diagonal brace. Now, the structural element that joins all the members are what we call joints or nodes. And the pitch is the slope of your truss. Okay, so next, let's discuss zero force members before we proceed with the different methods of truss analysis. Now, your truss analysis could be greatly simplified if one is able to first determine those members that support no loading. These zero force members may be necessary for the stability of the truss during construction and to provide support if the applied loading is changed. The zero force members of a truss can generally be determined by inspection, and they usually occur in two cases. Now, the first case, for case 1, So if only two nonlinear members or non-collinear members form a truss joint and no external load or support reaction is applied to the joint, the members must be a zero force member. As an example right here in our truss, so we have two non-collinear members being member AB and AE, and we have no applied loads and no support reaction. Therefore, we could assume that these two members are actually zero force member. As proof, we could isolate joint A and apply the equations of equilibrium to check or to solve for the forces in our members. And what we'd usually get, or what we'd get, are 0 for force AB and 0 for force AE. Alright? So another joint that we could consider is joint C, another non-collinear member, BC and CD. And if we apply our equations of equilibrium at joint C, we'd know that these two forces are actually, or these two members are zero force members. Now for case 2, if three members form a truss joint for which two of the members are collinear and the third member is a zero force member, provided that there are no external force or support reaction that is being applied to that joint. We have an example right here. So if we examine joint D, we have two collinear members being CD and DE, and there is no external applied loads or support reactions that is acting on our joint. Therefore, member DF is actually a zero force member. Another example here is that if member DF is a zero force member, if we examine joint F, so we have two collinear members right here, no applied loads, no support reactions. Therefore, joint CF is actually a zero force member. We could prove this by applying the equations of equilibrium to joint D and then to joint F, as shown right here as proof. Alright? So, let's practice identifying the zero force members in our trusses. Alright, so we have our truss right here, and it is supported at the ends, and then we have an applied load at this joint. So we're going to identify all the zero force members in our truss. So let's see it. So let's do with case 2. Since in case 1, there are no two member joints that we could see in this figure. So let's go with case 2. So we have here a collinear members, and then we have no applied loads, we have no support reactions. Therefore, this member is a zero force member. So let's highlight that right here. All right. Next, if we examine this joint, we have here a collinear members, and this is a zero force member, so we could disregard that. Therefore, this member is a zero force member. So let's highlight that. What else? Right, is at this joint. So we have two collinear members, no applied loads, no support reaction. Therefore, this member is going to be a zero force member. All right. Next, let's consider this joint. So we have two collinear members right here. This is a zero force member, so we could disregard that. No applied loads, no support reactions. Therefore, this member could be considered as a zero force member. So let's highlight that. All right. What else? So let's go to the other side. So we have here a two collinear members, and the third one is going to be a zero force member since there are no applied loads or support reactions at our joint. So let's highlight that. What else? So this one, two collinear members, no external loads, no support reactions. Therefore, this member is going to be a zero force member. All right. So two collinear members again, no external loads, no support reactions. This one is a zero force member, so we could disregard that. Therefore, this member is also a zero force member. All right. So what else? We could look at this joint. Two collinear members. This is a zero force member, so we could disregard that. Therefore, this member is also going to be a zero force member. So let's highlight that again. All right, so what else? So let's look at this joint. So we have two collinear members right here, and these two members are zero force members, so we could disregard them. Therefore, this member is also a zero force member. All right. And this joint. So we have two collinear members right here. This is a zero force member, so we could disregard that. Therefore, this member is a zero force member. Okay. Now, if this is a zero force member, this will also become a zero force member. So let's highlight that as well. All right, so what else? I think that's about it. Okay. So let's highlight all the members that have forces. So if you're going to examine are the different joints on the top chord, this member are actually going to have the same loadings, just like here, same loadings. And on the bottom chord, so this are going to have the same loadings. And then these members are also going to have loads, or going to be carrying loads. All right. So let's do another example right here. So again, we have our supports at the ends of our truss, and then we're going to have 4 applied loads on this joint, here, and here. All right. So let's investigate which members are zero force members. So we can start at this joint. We have two collinear members right here. No applied loads, no support reaction. Therefore, this one is going to be a zero force member. And then let's examine this joint. Two collinear members, a zero force member, no applied loads, no support reaction. Therefore, this one is also going to be a zero force member. What else? At this joint, no external loads, no support reaction, two collinear members. The third one is going to be a zero force member. What else? At this joint, two collinear members, no applied loads, no support reaction. Therefore, this member will also be a zero force member. What else? We could go to this joint. We have an applied load, therefore we can consider that this one. So no applied loads, no support reaction, two collinear members. The third member is going to be a zero force member. And then at this joint, we have two collinear members. No applied loads, no support reaction. This one is going to be a zero force member as well. What else? I think that's about it. If we examine this, 4 members, we can consider that. Here we have an applied load, just like here we have an applied load. Here as well, we have an applied load, even though we have 3 members right here. So those are those highlighted by red are our zero force members. Another example, so we have our truss here with supports at point A and G. So at point A we have a pin, and at point G we have a rocker, and then we have an applied load at joint E. All right. So what can we apply here? So we have a 2-member joint that has no external loads or no applied loads and no support reaction. Therefore, these two members are going to be zero force members. And then what else do we have? At joint H, so we have a 3-member joint. So we have 2 members being collinear. There is no applied loads at joint F or joint H and no reactions. Therefore, the third member is going to be a zero force member. So let's highlight that. I think that's about it. But if we examine our joints, so let's examine joint E. Although we have an applied load P, but if we examine it and apply the equations of our equilibrium, specifically summation of forces along the x-axis, we'd know that your force at ED and FE are going to be equal to each other. Therefore, if your member ED is a zero force member, your member FE is also going to be a zero force member. So let's highlight that as well. What else? If we look at joint G, so let's look at joint G. So joint G, this is a rocker. Therefore, we're going to have a horizontal reaction right here. And if we examine this joint and apply your equations of equilibrium, summation of forces along the y-axis, we'd know that your member AG is not going to be carrying any load. Therefore, that's also going to be a zero force member. Alright, I think that's about it. Okay, so let's start discussing the different methods that we could apply when analyzing our trusses. So the first one is the method of joints. So if a truss is in equilibrium, then each of its joints must also be in equilibrium. Hence, the method of joints consists of satisfying the equilibrium equations or equilibrium conditions of summation of forces along the x-axis being 0 and summation of forces along the y-axis being equal to 1 for the forces exerted on the pin at each joint of the truss. When using this method, it is necessary to draw each joint's free body diagram before applying the equations of equilibrium. Recall that the line of action of each member force acting on the joint is specified by the geometry of the members, since all our members are actually loaded to force members. As an example, let's consider our simple truss right here, and let's look at our joint B. So from this free body diagram, we have already isolated our joint B, and the only unknowns are the magnitude of the forces in the members BA and BC as shown here. So we have FBA as the force in member BA and FBC as the force in member BC. In our free body diagram, FBA, or the force in member BA, is pulling on the pin, which indicates that member BA is in tension, whereas FBC, or the force in member BC, is pushing on the pin, and consequently, our member BC is in compression. These effects are clearly demonstrated by using the method of sections. So if we cut our two members right here so that we could isolate joint B, as you can see in our new free body diagram, notice that the pushing or the pulling on this small segments indicates the effect of the member being either in compression or in tension. Typically, we start the method of joints or the joint analysis by selecting a joint that has at least one known force and at most two unknown forces. In this way, the application of your summation forces along the x-axis and the summation of forces along the y-axis yields two algebraic equations that can solve for the two unknowns. When applying these equations, the correct sense could either be assumed or investigated. For simplicity's sake and to avoid mistakes in solving, please note that I would recommend that we always assume that the unknown member forces to be in tension, that is pulling on the pin. If this is done, the numerical solution of the equilibrium equations will yield positive scalars for members in tension and negative scalars for members in compression. This is to avoid much of the mistake. So when solving, I would suggest that all the members will be assumed to be in tension. So when using method of joints, all the forces are pulling away from your pins. Alright, so the next method that we typically use is the method of joints, or rather the method of sections. So in the method of sections, we're assuming that since the is in equilibrium, therefore all its members must also be in equilibrium, and all the sections must also be in equilibrium. So the method of sections consists of passing an imaginary section through the truss, thus cutting it into two parts. Provided the entire truss is in equilibrium, each of the two parts must also be in equilibrium. And as a result, the three equations of equilibrium may be applied to either one of these two parts to determine the member forces at the cut section. So, if you guys would remember the equations of equilibrium, so what we're applying here is the summation of forces along the x-axis. So this must be equal to 0. Summation of forces along the y-axis, and this must also be equal to 0. And then the summation of moment at any point must also be equal to 0. So as an example right here, we're going to cut our section, our truss in or through members BC, CG, and GF. Therefore, we're going to have two parts of our trusses presented in this figure below. So once we have this figure, for example, we're interested in solving for the force in member GF, what we could use is the summation of moments at point C, and if we did that, we would only have one unknown, therefore we will be able to solve for this force. And going to the other side of our truss, if we're interested in solving for force BC, we could sum up our moments at point G so that we could solve for this force. Now again, for simplicity's sakes and for avoiding mistakes, we're going to assume that the unknown force members at the cut section are in tension, or all the members are going to be in tension. That is, the forces are pulling on the members. By doing this, again, the numerical solution of the equilibrium equations will yield positive scalars for members in tensions and negative scalars for members in compressions. So by doing this, when we apply our equations of equilibrium, whenever we have a positive sign or positive scalar, it would be under tension. And whenever we have negative, it will be under compression. Alright? So since we have two methods, typically we use method of joints when we are going to solve for all the member forces of our truss, and we use the method of sections when we're only interested in certain members of our truss. But sometimes we could use a combination of these two methods. Alright? Okay, so first example, we have here a sign that is subjected to a wind loading that exerts a horizontal force or horizontal forces of 300 pounds on joints B and C of one of the sides supporting the trusses. Now we're going to determine the force in each of the members of the truss and state if the members are either in tension or in compression. Now the first thing that we're going to do is we're going to visually inspect the truss if we could spot any zero force members. Now, let's look at here. We could apply case 2 in joint B. We have two collinear members, members CD and members DE. And there are no applied loads or support reactions at joint D. Therefore, this member is a zero force member. So we could highlight that as a zero force member. Alright. So next, Since we're going to be determining all the forces in all our members, we're going to apply the method of joints. Now, in choosing on which joint we should start, we're going to pick a joint that has at least or at maximum only two unknowns. And if looking at this figure, we could say that we have two unknowns at joint C. So we could start at joint C instead of having to solve for the reactions at joint E and A. So to avoid that, well, we're just going to start at joint E. So let's write it down here at joint, or rather at joint C. So again, we're going to start this by drawing the free body diagram of our joints. Right, so we have the free body diagram of our joint C. So for joint C, we have an applied load of 300 pounds, and the force on member CD is acting downwards vertically, and the force on CD is inclined or has a slope of 12 by 5. So this is by the principle of your similar triangles. So we have here a right triangle, and it has a hypotenuse of 13 feet, and the sides is 12 feet and 5 feet. So we're going to use ratio and proportion in solving for the components of our member CD for the horizontal and vertical components. All right. So let's start with the summation of forces along the x-axis. So we're going to assume a positive direction of acting towards the right side. So summation of forces along the x-axis must be equal to 0 for it to be in equilibrium. So let's start with 300 pounds. So that's going to be positive since it's acting towards the right side. And then we have the horizontal component of force CD. So that is going to be positive CD times 5/13. And the whole thing must be equal to 0 for it to be in equilibrium. So we have one equation, one unknown, solving for CD. It is going to be equal to negative 780 pounds. Since this has a negative sign, that means that our member CD is under compression. Right? So next, we're going to sum up the forces along the y-axis, and we're going to assume a positive direction of acting upwards. And it must be equal to 0 for us to be in equilibrium. So let's start with our force CB. Since it's acting downwards, this is going to be negative. And our force CD, or the vertical component of force CD, is acting downwards again, so this is going to be negative. So we have negative CD. And then for the vertical component, we're going to use 12/13. And the whole thing must be equal to 0. So we already know for CD from here. So we have one equation, one unknown. We can solve for CB. And that is going to be equal to 720 pounds. And since it has a positive sign, our member is going to be under tension. Since it's in our free body diagram, we're going to assume that the unknown forces in our members are all in tension. Alright, so let's proceed to the other joints. So where could we go? So we're starting at joint C. So if we proceed at joint B, we're going to have two unknowns. And if we proceed to joint D, we're also going to have two unknowns. I think it would be much more easier if we proceed with joint D, since the two unknown forces are actually collinear to each other. Alright, so we have the free body diagram of our joint D. So we have three forces. We have force CD, force DE, and force DB. And from our earlier inspection, we know that force dB is going to be equal to 0. All right. So what we're going to do is, instead of having our reference axis or reference x and y axis in this manner, we're going to tilt it like this. So let me just draw that in. So we have our y-axis here, and then we're going to have our x-axis right here. So we just tilted it. This is going to be 90 degrees, right? So from this free body diagram, we can now apply our equations of equilibrium. So what we're going to apply is the summation of forces vertical. So we're going to assume a positive direction of upwards, and it must be equal to 0 for us to maintain equilibrium. All right. So positive for CD, since it's acting towards the positive sign or positive direction of our y-axis, and then minus DE, since it's acting downwards, and the whole thing must be equal to 0. We have already solved for CD, and that is negative 780 pounds. So our DE now is going to be equal to negative 780 pounds. And since it's negative, this is going to be under compression, right? So I just rearrange our solution so that I would have more space. And continuing, so let's check first. So we have already solved CD, we have already solved CB, and DE, right? So we can now proceed with joint B. Right, so we have here the free body diagram of our joint B. So we have multiple forces acting on joint B. So we have CB, which we have already solved earlier. We have DB, which we have examined to be a zero force member. Next, we have our unknown force BA and our unknown force BE. Now, our unknown force BA, from the figure, our member BA or AB is inclined at a 45-degree angle. Therefore, this angle should also be a 45-degree angle. So let's write down our angle. So this is a 45-degree angle. Next, we don't know the inclination of member BE. So what we're going to do, from these two triangles, so this triangle is actually similar to this triangle. So what we're going to do is I'm going to solve for this internal triangle or internal angle. So let's name this as angle alpha. And what I actually need is angle theta. So this one should also be angle alpha. So solving for angle alpha, it is just going to be tangent alpha is equal to opposite 12 over adjacent 5. And angle alpha is now going to be equal to 67.38 degrees. Now solving for angle theta, our angle theta is just going to be equal to 180 degrees minus twice angle alpha. Since this is going to be a straight line, so this angle must be 180 degrees. And angle theta is now going to be equal to 45.24 degrees. All right. So let's write it down here. 45.24 degrees. All right. So we can now proceed in the application of our equations of equilibrium. So let's start with the summation of forces along the x-axis, assuming a positive direction towards the right side. And this should be equal for equilibrium. All right, so first one, we have 300 acting towards the right side, so that's going to be positive. And then we have the horizontal component of force BE acting towards the right, so that's going to be positive. So we have here positive BE. So we're going to use sine 45.24 degrees. Next, we have the horizontal component of force BA, which is going to be negative since it's acting towards the left side. So I have your negative BA cosine 45 degrees. And the whole thing must be equal to 0. So from this equation, we don't know anything. So we will not be able to solve anything from that equation. So let's proceed with the next equation of equilibrium, which is the summation of forces along the y-axis. So we're going to assume a positive direction of acting upwards. Alright, so first let's start with CB. Since it's acting upwards, it's going to be positive. And then we start with the vertical component of force BE. It's acting downward, so that's going to be negative. So we have negative BE. And this is going to be cosine 45.24 degrees. And then the vertical component of BA, so it's also acting downward, so that's also going to be negative BA sine 45 degrees. And the whole thing must be equal to 0. Now what I'm going to do is, let's rewrite this, or let's separate the constant. So let's write this as BE sine 45.24 degrees minus BA cosine 45 degrees. And the whole thing must be equal to negative 300. So this is going to be our equation 1. And then for our equation 2, this is going to be negative BE cosine 45.24 minus BA sine 45 degrees. And this is going to be equal to negative CB. And this is going to be our equation 2. So solving two equations, what we're going to use is our magic calculator. So let's bring out our calculator. So for our calculator, we're going to use our equation mode. So click mode, select 5 for the equation. And then we have two unknowns, two equations. We're going to select 1. Alright. So for A, from our first equation, it's going to be sine 45.24 degrees. Then for B, it's going to be negative cosine 45 degrees. And then for the constant C, it's going to be negative 300. Then from our equation 2, our A is going to be negative cosine 45.24 degrees. And then our B is going to be negative sine 45 degrees. And then for the constant, it's going to be negative CB, which is 720. So I have negative 720 equals. So we'll be able to solve for BE, which is equal to, right, so 289. So I think I made a mistake from our equation. So this is negative, negative. So let's check first. Right, so I think I made a mistake for A for equation 2. So this is supposed to be negative cosine 45.24. Right. So let's check that. Okay. So equal sign. So our x now, or our BE, is going to be equal to 296.987 pounds. So that's positive. So this is going to be under tension. And then BA is going to be equal to 722.493, and this is positive, so this is going to be in tension. Alright, so I think we've solved everything. So we have solved for BE and BA. So we have already solved all the forces on all our members. So let's just highlight our final answers. So we have DE here, CD, CB, and BE, and BA. Alright, so that's it for our first example. Next example, so we're going to determine the force in members GF, FC, and CD of the bridge truss zone in figure below. And then we're going to state if the members are either in tension or compression. We're also going to assume that all the members are pin connected. Alright? So in this type of problem, what we're going to use is the method of sections. It just so happens that all the members that we are required to find are already lined up. So we could just simply cut our truss right here. And we could either consider the left side or the right side. But looking at the left side, you would see that we have applied forces right here and more members to consider. We would also have two reactions at point A, while if we consider the right side, it is much more simpler. And also considering we only have one reaction at joint E, right? So I think it is safe to assume that we're going to be considering the left side, since it's much more easier to solve. Now the next thing that we need to take note of is the triangles, the similar triangles that we're going to be using when solving for the member forces. Now for this one, we are given these dimensions, 15 feet and 40 feet. Simplifying this, we'd have 3/8. Solving for the hypotenuse, it is going to be square root of 73. Likewise, in this triangle, it is going to be 30, and this one is going to be 40. Simplifying that, it is going to be 3, 4. And then solving for the hypotenuse, it's going to be 5. Right? So we're going to be using the similar triangles to solve for the components of our member forces. Alright. So since we're considering the left side, we also need to solve for the reaction at E. So let's draw the free body diagram of our left side first. There you go. So first, let's solve for the reaction at E right here. Right here. So let's name that as our, say, EY. So to solve for EY, what we're going to do is we're going to sum up the moment at point A so that we could solve for EY. And we're going to consider this whole truss. We are not yet going to use this free body diagram. So let's solve for EY. We're going to assume a positive direction of counterclockwise. Summation moment at A must be equal to 0 for equilibrium. Alright, so let's start with 15 kips. So it's going to rotate on a clockwise manner. So this is going to be negative. The perpendicular arm is going to be 40 feet. So we have negative 15 times 40. Next, we have 10 kips. Again, clockwise. So this is going to be negative. Perpendicular arm is going to be 80 feet. So we have negative 10 times 80 feet. Next, we have our EY. It's going to rotate on a counterclockwise manner. So this is going to be positive. And the perpendicular distance, it's going to be 160 feet. So that's positive, oh, sorry, positive EY times 160 feet. And the whole thing must be equal to 0. So we have one equation, one unknown. You can now solve for EY. And it's going to be equal to 8.75 kips. Alright. So now that we know the reaction at EY, we can now use this free body diagram to solve for our unknowns. So we have three unknowns. So again, what I'm going to do is I'm going to assume that all the members are in tension. So we have three unknowns, GF, FC, and CD. Right? So I've already placed the similar triangles for our forces. So where should we start first? We could start with summation moment at C so that we could solve for GF, or we could start with summation moment at F so that we could solve for CD. I think that's the easier path, no? So we'll start with the summation of moment at F so that we could solve for CD. Let's start with that. So wait, we're going to assume a positive direction of counterclockwise summation of moment at F, and the whole thing must be equal to 0. Alright, so our CD is going to rotate on a clockwise manner, so that's going to be negative. The perpendicular distance is going to be 15 plus 30, 45 feet. Alright, so that's negative CD times 45. Or rather, sorry, this is going to be 30 feet. So times 30, right? The next EY is going to rotate on a counterclockwise manner, so that's going to be positive, and the perpendicular distance is going to be 40 feet. So we have positive 8.75 times 40, and the whole thing must be equal to 0. Now we have one equation, one unknown. We're going to solve for CD, and it's going to be equal to 11.667 kips. So it's positive, that means it is under tension. Alright, so maybe we could move this a bit so that we could have, we could have more space. Alright, so let's proceed. So the next thing that we could do is we could either sum up all the horizontal and then sum up all the vertical forces. So we'd have two equations and we'd have two unknowns, GF and FC. Or we could sum up the moment at point C so that we could solve for GF. So let's do that. Let's sum up our forces or sum up our moment at point C. So we're going to assume a positive direction of counterclockwise, and everything must be equal to 0 so that we could have equilibrium. So we're going to have first the horizontal component of GF. So it's going to rotate on a counterclockwise manner, so that's going to be positive. The perpendicular distance is going to be 30 feet. So that's going to be positive GF. Then we're going to use 8 divided by square root of 73. Then for the perpendicular distance, that's going to be 30. Next, the vertical component. Again, it's going to rotate on a clockwise direction, so that's going to be positive. And then for the perpendicular distance, it's going to be 40 feet. So we have here positive GF times 3 divided by 73, square root of 73, times 40 feet. Next, we have EY. It's going to rotate again positive counterclockwise direction. And the perpendicular distance is going to be 80 feet. So we have here positive EY times 80 feet. And the whole thing must be equal to 0 for us to maintain equilibrium. So we have already solved EY earlier, which is 8.75. We only have one unknown, which is GF. So we have one equation, one unknown. Solving for GF, we'd get negative 1, 6.613 kips. And since this is negative, that means that our member is under compression. Alright? So next, we could proceed to either summation of forces horizontal or summation of forces vertical. So I think I'd go with the summation of forces vertical. So let's sum up our forces vertical. So assuming a positive direction of acting upwards, and everything must be equal to 0 for us to maintain equilibrium. Right? So our GF is acting upwards, or the vertical component of GF is acting upwards, so that's going to be positive GF. We're going to use 3 all over square root of 73. And then next, our FC is acting downwards, so that's going to be negative FC. And we're going to use 3 all over 5. And then we have our reaction EY acting upward, so that's going to be positive EY. And everything must be equal to 0. So we have already solved for GF, we already know EY. So we can now solve for FC. So our FC is going to be equal to 4.861 kips. And it is positive, that means it is under tension, right? So let's highlight our final answers. So we have CD and GF and FC, right? So that's it for our example. Right, so next problem, we're going to determine the force in members GF, FC, and CD of the cantilever truss shown right here. And then we're going to say if the members are either in tension or compression. We're going to assume that all the members are pin connected, right? So first, let's establish some dimensions first that we are going to use in our solutions. So let's start with these dimensions. So we could solve that by using this big right triangle right here. So this is going to be 6 and this is going to be 3 meters. So solving for the hypotenuse, it's going to be 3 square root of 5. And then dividing that by 3. So this are going to be square root of 5, square root of 5, and square root of 5. Alright, so let's write that down. So this is square root of 5 meters, square root of 5 meters, and square root of 5 meters. Next, we're going to need this internal angle theta. So we could solve that by using our tangent. So solving for angle theta, it's going to be tangent theta is equal to opposite 3 meters divided by adjacent 6 meters. Therefore, angle theta is going to be equal to 26.565 degrees. Alright. So we're supposed to find the forces in these 3 members. So what we're going to do is we're going to apply the methods of section and cut our truss here. Alright, so let's draw the free body diagram for that one. Alright, so we're going to assume that all the members are in tension, so they are pulling away from our section. So this is GF, this is CF, and this is CD. Right? So if you want to be able to solve for something and with less complications, I would suggest that we take summation moment at joint A, so that we don't need to consider GF and we don't need to consider CD since they are concurrent at point A. So we could solve for CF. Right, so let's do that. So summation moment at A, we're going to assume a positive counterclockwise for the rotation. Summation moment at A must be equal to 0 for equilibrium. Alright, so let's start with our force, applied force, 12 kilonewtons. So it's going to rotate on a clockwise direction, so that's going to be negative. And then for the perpendicular distance, it is going to be square root of 5. So we have here negative 12 times square root of 5. Alright. Next, we have CF, and it's going to rotate on a counterclockwise manner, so that's going to be positive. And the perpendicular distance is going to be 4 meters. Right? So that's positive CF times 4 meters. And the whole thing must be equal to 0. So we have one equation, one unknown. We can now solve for CF. And that is going to be 6.708 kilonewtons. And that's positive, so that is going to be under tension. Alright? Now that we have solved CF, what else can we do? Right? So next we could sum up moments at point F. So this is point F. This is F. Right. So if we sum up moments at point F, we could solve for CD. Right? So let's do that. So we have here summation of moment at F, positive direction, counterclockwise. This must be equal to 0 for equilibrium. Right? So let's start with 12 kilonewtons. So it's going to rotate on a counterclockwise manner. So that's going to be positive. And then the perpendicular distance is going to be 2 times square root of 5. So we have positive 12 times 2 square root of 5. Right? Next, we have 12 kilonewtons. And it's going to rotate again on a counterclockwise manner. So that's going to be positive. And the perpendicular distance is going to be square root of 5. So again, positive 12 times square root of 5. Next, we have 4CD. It's going to rotate. So again, on a counterclockwise manner. So that's going to be positive. And the perpendicular distance is, we don't know. So let's find out what is the perpendicular distance. So from the given, this is 3 meters. And so let's change, oops, sorry. So let's change this first. So this is 3 meters. Now, we have this big right triangle and then this small right triangle. Now we know that they are similar triangles. The big triangle has a base of 6 meters and the smaller triangle has a base of 4 meters. By ratio and proportion, we can solve for the height of our triangle. And that is going to be 2 meters. And then this one is going to be 1 meter. Right? So again, if we rotate angle CD by point F, so it's going to be positive counterclockwise. And the perpendicular distance is going to be 2 meters. Okay. So let's write that. Positive, oops, sorry. Positive CD times 2 meters. And the whole thing is going to be equal to 0. Right? So we have one equation, one unknown. You can now solve for CD. And that is going to be equal to, that is negative 40.249 kilonewtons. So since that is negative, that means our member is under compression. Alright, next. We already know CF and we know CD. So what we could do is we could either do a summation of forces along the x-axis or a summation of forces along the y-axis. Either way, we will be able to solve for GF. So maybe let's use summation of forces along the x-axis. Alright, so let's write that. We're going to assume the positive direction towards the right side. Summation of forces along the x-axis must be equal to 0 for equilibrium. Now, alright, so let's establish the angle of our applied loads. So we know that this is angle theta. And what we need to find is this angle right here. Alright, so first let's establish our angle. So we have here angle theta, and this angle is 90 degrees. Therefore, the angle here is going to be 90 minus angle theta, right? But if you look at here, this is also 90 degrees. And if this is 90 degrees, and this internal angle is 90 minus theta, therefore this angle is going to be equal to theta, right? So this is also angle theta, right? So we're going to use that to solve for the components of our applied loads. Alright, so let's start. So for the horizontal component of our forces here, so it's going to be 12. So it's going to be positive since acting towards the right side, same as this one. So we're going to have 12 sine theta. And there's going to be two of them, one here and then one here. So we could just multiply this by 2. Alright? Maybe let's do that a bit more clearly. Let's move this here and we're going to multiply that by 2. Right? What else? Our 4CD is acting towards the right, so that's going to be positive as well. So positive CD. And then the horizontal component of GF is also going to be positive. So we have here positive GF. And then this is also going to be theta. So the horizontal component is going to be GF cosine theta. And the whole thing must be equal to 0. Alright? So we already know CD from our previous solution. We know theta. Theta is going to be 26.565 degrees. So we can now solve for GF. And our GF is going to be equal to 33 kilonewton. And that's going to be positive, so that means it is under tension, right? So that is the final answers for our problem.